Okay, I'm back. Am I now audible?
Yes, Kak.
Thank you. Okay, thank you. So sorry for using up like 2 minutes in the beginning. Good afternoon, everyone, and welcome to the last session of this school, the presentation session. So this is actually the peak of this school where you will be presenting your work. And I'm not going to present the rule anymore since Lano had presented it in the morning. So let's get started right away. Could you raise your hand if you're part of group 1? I just want to know if everyone here at the moment. Right, perfect, thank you. Now you can lower your hand. And what about group 2? Could you also raise your hand, please? Group 2. Okay, I am seeing fewer people. Thank you. Please lower your hand. Now, group 3. Group 3. Right, perfect. And then now for group 4, please. It's group 4 here. Okay, now for group 5. Could you raise your hand, please? Thank you. And then group 6. Perfect. And the last group, group 7, please. Okay, thank you. Since everyone is now here, then let's get started right away. Well, actually, we are going to draw the order of the presentation, but since group 1 requested to have their presentation come first, so let's welcome group 1. Group 1, are you ready to present your work? Do you have the permission to share your screen?
Yes, I will share my screen right now.
Okay, thank you for that. And let me check. Is Dr. Luki here? Okay, already with the scoring, right? Yes, I suppose that's a yes. Okay, I'll take that as a yes. Right, so please welcome group 1 for the presentation. Group 1, the screen is yours.
Okay, hello, good afternoon, everyone, and welcome to our presentation. So, first of all, I would like to thank all of you for coming here. Also, I would like to thank the organizer and also the lecturer for giving us an opportunity to doing this presentation. So, as you can see in your screen right now, our topic today is solve ODE with finite follow method using PyPy. But before we start, let me introduce myself and also my team members. We are from Group 1. My name is Yulia Arsishano, but you can call me Archie. And today, I won't be alone because I will be accompanied by my teammates, namely Hiskia, Ferry, Bisma, and also Sabrina. And this is our outline of our presentation today. So first we will talk about what is ODE means, and then we will talk a bit about numerical method, and then PyPy. And our highlight topic today is solving ODE with PyPy. And then we will show you what will happen if we run PyPy, and then we'll jump to a conclusion. And then at the end of the presentation, we will have like a short Q&A session. So I hope you guys listen to our presentation carefully. So if you have any question, maybe you can save it and ask us at the end of the presentation. So without any further ado, let's start the presentation. And the first we will be it will be explained by my friend.
Okay, good afternoon, everyone. First, we will find out what ODE is here. What is ODE? In mathematics, the term of ordinary differential equation, also known as ODE, is an equation that contains only one independent variable and one or more of its derivatives with respect to the variable. In other words, the ODE is represented as the relation having one independent variable x, the real dependent variable y, and with some of its derivatives. Okay, can you next, Archie? Okay, the order of ODE is defined to be the order of the highest derivative that occurs in the equation. The general forms of nth order ODE is given as the equation below, you can see in your screen. And nth order ordinary differential equation is linear if it can be written in the form you can see in your screen. Okay, maybe can next search. Okay, and then ODE has a remarkable application, and it has the ability to predict the world around us. It is used in a variety of disciplines like biology, economics, physics, astrophysics, chemistry, and engineering. It helps to predict the exponential growth and decay, population, and species growth. Some of the use of ODEs are modeling the growth of diseases, describes the movement of electricity, describes the motion of the pendulum, and then waves, and then used in the Newton's second law of motion and the law of cooling, and then n-body problem. Okay, next, Archie. Okay, then we will explain both numerical method and will explain by my friend Ferry.
Okay, so I'll explain about the numerical method. So numerical method is an approximate computer method for solving a mathematical problem which often has no analytical solution. A numerical method is said to be consistent if all approximation of finite difference, finite element, finite volume, etc. of the derivatives tend to the exact value as the step size, delta t, delta x, etc. tends to 0. Okay, so numerical analysts and mathematicians have a variety of tools that they use to develop numerical methods for solving mathematical problems. So to solve common division problems, we can use the Euler method, clear and vague methods, the Euler-Backrode, trapezoidal law, and the Runge-Kutta method. Next. Okay, so aside from solving differential equations, we can also use numerical method to solve integration with the Newton method, Simpson's law, and trapezoidal law.
In astronomy, we are playing with big or massive data, so it's kind of impossible for us to doing a numerical method like just what Ferry said before, manually. So we need a tools, and one of the tools that I was talking about is VPy. So VPy is an open software framework designed to facilitate the sharing of simulation codes for microstructural evolution. VPy is an object-oriented partial differential equation or PDE solver written in Python and based on a standard finite volume approach.
All right, next, so back to what actually our problems are. So we were given an assignment to solve this equation, which is the ODE or ordinary differential equation that my friend Bisma just explained before. So based on the problems, we do have a question dy over dx equals to fx equals to tx squared, and we have to solve that question, which the requirement is y0 equals to y0 equals to f0 equals to epsilon, and which is about 0. Next. So yeah, so based on the explanation that Ferry or my friends will explain before, that the numerical method that is used to solve our problems, we do need delta value. In here we just use the dx value, which is has to be close to 0, or in here we use 0.1, and in x equals to 10. So the first one what we do is we have to use the 5 to solve this question by, or first of all, we in here in our research or our GA, we actually use 5, and we have to solve the question by using Google Colabs. The first one of what we do is we install the 5 because before we do it, actually Google Colab has know the FreePy itself. So we install it and we call the FreePy library, and we do like solving the ordinary differential equation. We put the constants dx and nx, and we solve it. After we solve, we got the results of a range or array value of x and y that you can actually see on the screens. And after we got the value, we actually do the polynomial regression to get the value of y, because before we just have the dy per dx value, which is equals to 3 times x squared. And yeah, we use the order of the polynomial is 6. And after do it, we show the plot of the graph of the that equation that we can actually on the upper sides on the screens. And there are about 10 dots there, and there's a line which is the polynomial regression. And after that, we print the p-value. And what does it mean by printing the p-value? It means actually to solve or to get the equation of the polynomial regression. Next. So yeah, I'm sorry, it's quite late. Another example of for question number 1 is we have to use the dx value, which is about 0 as well, but in here the case is smaller than before, like the dx value from 0.1 and now is 0.01, and actually is constant. So yeah, we do actually literally the same before with using the dy per dx question 3 times x squared, and we got the result x and y range or array. But in here we just wanted to make it clearer by put a number 1 in after the x and y in order to not confusing the Python itself. So we do plot it by, yeah, this is actually a simple code. And yeah, after that we do polynomial regressions, and we plot the x1 and y1, and with the order of polynomial regression is 6. And yeah, you can actually see on the screens on the upper sides, there are about 10 dots and lines, which is approximation of polynomial regressions. And after we printed the p1, we got the equation which the variable value with dx equals to 0.01. Yeah, you can actually see on the screen. Next. So that was actually the first question. For the second question, we are asked to solve or display the diffusion mass 2020.py. We solved this question by using terminal on our computer. So yeah, for the first one, we actually got that file, and we kind of differentiate the value of variables for dx, dy, d, and nx. So for the first cases, we do have dx equals to 1, dy equals to dx, which is 1, d equals to 1, and x equals to 20. So for the what does actually it mean? So it actually for the x-axis value or range, we times dx, we multiplicate dx by nx. So it is actually 1 times 20, and for the y-axis, it is dy times nx, which is 20 as well. So for the second cases, we actually do literally the same things, but we have different value of variables. And here we use dx equals to 2, dy equals to 3, d equals to 1, and x equals to 20. You can actually see on the x-axis is actually the multiplication of 2 of dx times nx, 2 times 20, which is 40. And for the y-axis is dy times nx, 3 times 20 is 60, of course. So next. So for the cases number 3 and 4, yeah, of course we did the same thing, but we differentiate the value of variables, right? So you can actually see on the axis and y-axis, which is the multiplication of dx time nx and dy time nx. So yeah, you can actually see the gradient. We call it gradient of color. And for the number 4, yes, it is actually literally the same as before. But in our conclusion in here, so we kind of like don't find any difference between the distribution of the color or the gradient of the color. All right, so next.
And for the conclusion for problem number 1, firstly, from the insertion of the equation, we have to take the value of y0 equal to epsilon is close to 0 is almost equal to 0. For different value of dx and nx will give different equation of y. Next. And for the problem number 2, we can conclude that the numerical method can be used to solve the two-dimensional diffusion problem and any other two-dimensional ODE. Different values of variables will give different gradients.
And here's the reference for our presentation today. And I think that's all from our slides. And now I think we'll be moving on to Q&A session. So if you have any question, maybe you can type it on chat box or you can freely open your mic.
Okay, I have a question.
Yeah.
First of all, I want to know the second assignment of your what is it? Can you explain what is it actually?
So all right, so I will answer my question. Thank you for your question. So we are actually, as I said before, like we are asked to display the diffusion mass 2020 py on that file. If you access that file, there's equations, and yeah, after you kind of like run it on your terminal or by using Atlas, probably you can do it as well. You got the result of the picture. The picture is actually related to FIFA itself, like the modeling. And here the case is color. So we kind of like making the gradient of the color itself. Like you can see actually the y-axis and the right side. So it describes what if we change the variable's value. So we got the color of the gradient. So this is actually the explanation of that.
Oh, okay. But I'm wondering about the physics of what you're doing here. You're showing a graph without explaining what the graph really is. It's just a number and a gradient. Can you tell more about what is it supposed to mean?
Yeah, it's actually a tough question. Thank you for your question. Yeah, we, to be honest, we don't actually kind of like do understand about what actually it is, but yeah, to be honest, we don't know the physical meaning of that. All we know that we do have a question. We plot the question to get the result of this picture, but we do not actually understand what physical thing that is related to. I'm sorry.
Okay. Thank you for the answer. Maybe I can give some correction. I believe it's a diffusion and it's not an ODE, right? It's a PDE.
Yeah, it's diffusion.
And phi is used specifically to solve PDE. So from the beginning, you already misunderstood the power of phi. The first assignment is to solving ODE. It was used just for example how phi can be used to solve ODE. But the most important feature from phi is to solve PDE. You can see in their web page. Maybe that's all I can give. Thank you.
Thank you for your correction. Actually, we don't actually understand about this, so thank you. Is there anyone who wants to give some topic to discuss again?
Okay, can I ask?
Sure.
All right. Okay, can you go back to the first code that you have shown to us, the one that you saw for the, what we call it? Yeah, this one that you saw from polynomial regression. Okay, so here you explain that you solve some function here and the equation is given below here. So here, can you relate what are the relationship between your ODE and also your polynomial regression here?
So thank you for your question. I will answer that question. So we do have the ODE question, which is equal to 3 times x squared in here, and we do use polynomial regression in order to kind of like get in the equation of from the x and y points. So basically we use the polynomial regression by using the x and y points. So that's what actually we did.
Okay, so what are the ODE technique that you use to solve for this problem? Yeah.
All right. So it's kind of like, it is my assumption, like we want to get the y equation from the differential equation. So the technique we use in here is actually the integration, if I'm not mistaken. So we got the integration. We use the integration to get the y function or y equation.
Okay, so just one last question. I want to ask that you say that you install FIP, but I cannot see anywhere in the code. This probably using the FIP pi here. That's all from me. Do you get my answer? My question. I saw.
Yeah,
that
I got you.
Yes.
That is actually quite clear. Yeah. First of all, we kind of like calling the phi pi itself, but in here there's a function or there's a library that is called cell centers, and whatever it is and which is written in there. But when we don't use the phi, we kind of like we cannot use or that function. It's gonna be error. But when we use phi itself, it does work. Yeah.
Yeah. So because like this question, you can use like Newton, Raphson, or Ranskota calling from the SciPy and then solve it directly. No need to call the complicated function. So that is what I'm saying, that some kind of missing technique here. So from there, you just call another SciPy regression and you will have like a shorter solution for this one. Okay, that's all my comment for this one. Thank you.
Okay, thank you, Dr. Lisa.
Thank you. Maybe I'll be taking over since the time is up for this group, but just one quick question. Can you give maybe a brief, not explanation, but an answer about the calculation time when using PyPy? Like how long did it take for you to, like finish all of this calculation? Is it in the order of seconds, for example?
I think it's seconds. Yeah.
Okay, thank you. And maybe further discussion can be done, behind the scene. So yeah, please, if you have any more questions or discussion, then please reach out to group 1. And let's give applause to group 1, maybe virtual applause. Thank you, group 1. And you can stop sharing your screen. All right, so thank you everyone for the questions. Very interesting discussion. And we're going to move to the next order of the presentation. Initially, I was going to draw by using some kind of a random number generator, but here it is. Group 4 had booked the slot for this session. So please welcome group 4 to the stage. And if you're ready, then the screen is yours. Group 4, you ready for the presentation?
Yes, I'm ready. We are ready.
Right. Okay, cool. Please just take over the step.
Okay. Good afternoon, ladies and gentlemen. We are from Group 4, and now we're going to present about our report of conduct numerical experiment using rebound. These are the topics that we're going to talk today. The first one is the brief definition of n-body problem, and then the numerical methods for tools to attack n-body problem. After that, there is the explanation of rebound, data processing, including the details of our dataset, and the last one is conclusion. First, I'm going to talk about the n-body problem. So what is n-body problem? In physics, the n-body problem is the problem of predicting the individual motions of a group of celestial objects interacting with each other gravitationally. That is the general equation of the n-body problem, where the first part of the equation is the time term, where we can find the time variable for the second derivative of position, and the second part is the gravitation term with the non-gravitation term. The analytical solution for the two-body problem exists, but that it has become intractable for the three-body problem. Fortunately, it is possible to solve a simplified case of general problem with restricted three-body problem, where two bodies in elliptical orbit about their center of mass, and the third body with biggest mass. So numerical simulation is needed to studying system of three or more objects. An orbit is uniquely stated by 6 orbital elements. There is 2 orbital elements in small solar system bodies, Cartesian and Keplerian. The Cartesian orbital elements are position, x, y, z, and velocities, vx, vy, vz. However, the Keplerian orbital elements are the semi-major axis, eccentricity, inclination, the longitude of ascending node, the argument of barycenter, and the argument of barycenter. There is also mean anomaly, usually for planet and asteroid, and the time of barycenter passage, which is symbolized by tau for comet. On this occasion, we used the Keplerian one to represent the rotating coordinate system.
Hello everyone. So now I'll be talking about the numerical method that was employed in our analysis. So moving on to the next slide, please. Yeah. So as was already discussed by my previous colleagues in group 1, that numerical method has various advantages over analytical method, especially when analytical solutions are not possible. So what we are trying to do in our n-body simulation today is basically we are trying to find out their orbits and the paths that they are going to follow. So instead of doing a continuous integration from point A to point B, what numerical method does is that it breaks the whole path or the curve into small units, which is called discretization. So as you can see in the image over here, you have a smooth curve, and integration would basically find the area under the whole curve. But what we can also do is approximate the curve by a number of rectangles. So you would also notice that the smaller the rectangles are, the more closer will be the value to the actual value. And if I increase the size of the breadth of the rectangles, the errors would also increase. So basically, these rectangles could be called the time step in our particular analysis. So the kind of value that we're going to get very much depends on the time step that we're going to use. So to formulate an numerical method for the n-body problem, there are 3 steps that we are going to follow, which are shown in the next slide. Yeah. So for any physical phenomena to be understood by a numerical method, there are 3 steps, of which the first is to understand the physical reality. The second is to come up with a mathematical model to explain what is happening. And the third is to discretize the model. So when I say understanding the physical reality, I mean identifying the forces that are at play in the particular system that we are talking about. So in our n-body problem, the force that we are going to consider is the gravitational force. Now, once we identify that force, we also have to identify how that force mathematically works. So over here, you can see the image. We have the Newton's formula for gravitational force, right? So as we can see, it depends on the pair of objects and the masses and the distances between those objects. So once we have the force, we are able to build basically the equations of motion and also come up with how the system evolves with time. Now, once we have that, it's going to form a particular equation, and it's going to form a curve if I analytically graph that equation. But what we're going to do is we are going to divide it into small steps. So basically, instead of directly and smoothly going from point A to point B, I'm going to take steps of some reference time, which could be depending on the timeline of our system. It could be 1 second, it could be 10 years, it could be 100 years. It depends on the system that we are trying to analyze. And depending on those time steps, we can find the value after every time step that has passed, which gives us data points that can be plotted into the full path of the system. So moving on to the next slide. So in our particular system, as I've said, that gravitational force acts in pairs. So it's independent of the presence of other pairs in the system. So what we mean by that is that the superposition principle is followed. So as you can see on the image, if we have 5 particles, each particle interacts with the other 4 particles, right? So when we come up with the number of pairs, it's of the order n into n minus 1, which is approximately n squared. So that is the order of discretization that is going to be followed. So now that we've understood the numerical method that we're going to use to calculate the orbit, I'll be handing it over to my colleague Gading so that she can explain about the rebound package. Thank you.
Okay, so we are going to explain about rebound. So what is the rebound? Rebound is, we can call it like the n-body integrator or software and package, and it contains the particles that represent objects in space, such as suns, moons, any dust of particles, and etc. It is very flexible and can be customized to many problems in astrophysics, and it can be used via C and Python interface. So for the beginners, it is quick and free to use with Python. Okay. Knowing more about rebound, there are some structures and modules that we have to know. The structures, there are simulation structure. It's all the configuration and status and particle data of one rebound simulation. And the particle structure is for only one particle in a simulation. And the modules are the gravity solvers, collision detection algorithms, boundary conditions, and integration methods. Okay. From the modules that we know, what is our goal with rebound? We have to visualize the orbit of planetary and asteroids. And we have to know, and we have to get the parameters that we want, and it will be explained by my teammate, Theo.
Okay, the next one is the data processing. First of all, we collect the data from the website called ssdtplnasa.gov. In that website, we can collect the data for the asteroid, but we have to input the parameter first, like inclination, semi-major axis, and then the eccentricity. For the asteroid, next we use the same website, but the differently we collect the data for the planet with the planet and planet, but with the same Julian date. Okay, as you can see in the ssdtplnasa.gov, first we collect the asteroid data. we can choose what kind of object that we want, but we choose the asteroid. We choose the asteroid, and then limit by orbit class. We choose the trans-Neptunian object. Okay, and then we can customize object or orbit constraint. Like we use the eccentricity greater than 0.05, and then we can choose the semi-major axis right within the range 39 to 40, and the inclination greater than 30 degrees. And then after that, we just apply output for the basic of asteroid, and we add the date, Julian date, the epoch, and we add the anomaly, mean anomaly, and we get the data. As you can see, in the epoch is all the same, and A is the semi-major axis, E is the eccentricity, I is for inclination, OM is longitude of ascending node, the W is for argument of y-axis, MA is mean anomaly, and XYZ and VX, VY, VZ is the 6 orbital element for the Cartesian coordinate. Okay, the next slide is once we get the asteroid data, we use the same epoch and we collect the planet data. As you can see, the epoch is the same as the asteroid. Actually, the data is provided by Dr. Budi Darmawan. We have experimenting our own data. I have collect my own data, but the plot isn't that good. Isn't that good rather than this? So I choose this data instead. Okay. Next part will explain by Santana.
Thank you. So now that we understood that what we've done and what are the packages we've used, let's see what the results are that we got. So as was the objective of our analysis, we wanted to calculate the orbital parameters and basically see how the orbits change or evolve with time. So we took the primary as sun. And over here in the center of the images, where on the right, you can also see a star over there. So that is the location of the sun. And on the left, we can see the orbits of planets, which seem very, they seem to be in the same plane and something that we are already aware of. But if we look at the orbits of asteroids, we can see the chaos that is present in the system. So moving on to the next slide. So over here, you can see both the planets and the asteroid orbits together. So the X and the Y axis are basically spatial coordinates in astronomical units, which is the average distance between the Earth and the Sun. And the three images that we see over here are from three different viewpoints. So on the top, the image is on an edge-on view. So if we look in the center, there's a glowing yellow sphere, that's the sun, and we can see a line that passes right through the middle, which is actually the orbits of the planets. Although the orbits that we see at high inclinations are actually the orbits of the asteroids. On the bottom left picture, we see a top view of the same. So now we can clearly see that there is no actual line passing through the sun, and it's actually the concentric orbits of the planets. And again, we have the orbits of asteroids, and the same thing on the bottom right from a different angle between the edge-on and the top view. So moving on. So this is over here. If you want the codes for this particular presentation that we did, you can ask us for the presentation. We'll share it with you. So you have this link over here to the codes directly also. And with this, we come to the end of our project presentation. And thank you so much. So if there's anyone who wants to get in touch with any of the team members, we have our emails. And now I would welcome any questions for me and my team members. Thank you.
Right. Thank you, Group 4, for the very nice presentation. Any questions or discussion from the audience?
Okay, maybe I have questions.
Yes, please.
I want to ask maybe about the time scale of this integration. How long? The time scale?
Sir,
Okay.
Yeah.
Okay. Actually, this is time integration for 100,000 years, but I have wrong code. So the output is the plot of the orbit. We don't track every year or of the orbit. So actually, this is integration for 100,000 years.
100,000 years. Okay. And then I want to know what is the end goal of this project? What do you want to get from running the rebounds? The insight maybe.
If I can answer the question, I think so. The point of using softwares like Rebound, and especially in particular with our analysis, is to see that whether the gravitational interaction that presents in our system does it lead to a balanced system where the orbits go on for a long time, or a system that uh, there are a lot of possibilities. So the particles may break free or they may fall into the center. So it's to analyze that possibility for the future.
Yeah, that's interesting. That's one way to see the wonderful use of rebound. So you can explore like whether an asteroid still bound or getting kicked out from the solar system or else. And last, maybe I can comment something from these slides. You put the conclusion here, but it's actually not a conclusion. It's the results of the rebound. So if you want to put a conclusion, maybe you can put something like using rebound, you can get blah, 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 something like that. So it's a mismatch, I think. Okay, thank you.
Thank you. Thank you. Yes, we appreciate the last feedback. Thank you.
Thank you. Any more questions from the audience, or maybe comments, suggestion? And by the way, the participants are also allowed to ask questions. So no worries, guys. You are not betraying your friend if you're asking questions here.
Can I ask a question maybe?
Yes, please.
Yeah. Yeah, thank you for the presentation. It's very nice. I just want to ask concerning the method. What kind of method do you use for the integration?
So actually, while reading about the Rebound package, I was going through what integrated uses. So it was IAS 15, and I tried to read a little bit about it, which it says that it basically what it does is that the time step is not constant, and in what I understood is it keeps getting modified based on the result, and it's a non-symplectic integrator, which what I understand by a little, just a small search, is that it's a system where energy is dissipated, but my knowledge on the specific integrator used is limited to that.
Okay. Sorry, my connection is low. What name of the integration?
So actually, if you go to the Rebound's website, so it calls the integrator as IAS 15.
Oh, yes.
Okay. Yes. So basically what it is that the time step that is used keeps changing based on how the system is evolving. And there is dissipation of some parameter included in the simulation. So this is what I could understand a little bit from what was written and a small search. So yeah, that's the limited knowledge.
Okay. Yeah. Yeah. Maybe I just want to have the short comments regarding the presentation. In the analysis of dynamical asteroid, you can, people usually use the Kepler's semi-major axis, eccentricity, etc., and see the evolution of it. And as you can see, for example, in the figure, we can see some of the asteroids move inward toward the suns, and maybe some others go toward the solar systems. And if we can see this evolution of semi-major axis, for example, we can see clearly that this asteroid go to inward the sun, so go outside the solar system. So I think maybe better if you put the plot, show the plot for the semi-major axis or inclination or eccentricity. I mean the evolution of that orbital parameter. Okay, that's all. Thank you very much.
Thank you. Yes, I agree with that. We could have included those plots. Thank you.
Awesome. So thank you, and let's give a round of applause for group 4. Maybe a virtual applause will do. Thank you, group 4, and you can now stop sharing your screen. Thank you for such a very inspiring presentation. So now we turn out that we have the order set because everyone like coming up to say, hey, I want to go next. So now let's welcome group 5. You said that you'd like to go next after group 4, right? Are you ready for this? Anyone from group 5?
Yes, we're ready.
Okay, perfect. Then please share your screen, and after this you can start right away. And for example, if you start in the Q&A session, then you can also take over the session. So please feel free to ask the audience whether they have any questions or not. Right. Okay, so the screen is yours.
Can you see my screen now?
Yep.
Okay, so is the screen visible to everyone? Okay, so I will start. So hello everyone. Good morning, good afternoon, good evening, or maybe good night at some place. So myself Shubham Bharadwaj, and I am from Group 5. Me with my other team members, Garini, Abrar, Haru, Farah, and Nora, are going to give a short presentation on TARDIS, which is a spectrum modeling tool. So on the first slide itself, you see there are two figures. Haru, the slides are not correctly visible. It's shifted towards left. Yeah, now it's okay. Oh, sorry for the interruption. Okay, so on the first slide itself, you guys can see two images. The left one is very beautiful, colorful image. So it's a supernova remnant of some supernova, and 103b, which is taken by Hubble Space Telescope, HST for short. And on the right, we can see the spectrum of a type 1a supernova, 1998 AQ. It is a type 1a supernova, and this spectrum is taken basically after 1 day of the maximum light in optical band, which is in particular filter in B band. So why we are just showing this supernova remnant and supernova spectrum is because TARDIS is basically built to generate spectrums or to make spectrums of supernova by some simulations. Okay, so can you go to the next slide? Yeah, so here's the outline of our presentation. First, we are going to tell what is TARDIS, and then we are going to tell why we use TARDIS, and then how it works, and then we'll go to the TARDIS tutorials, and then in the final slide we'll show you the simulation results. The next slide, please. Yeah, okay. So what is TARDIS? So TARDIS basically stands for temperature and radiative diffusion in supernova. So here the supernova word is explicitly used because the TARDIS has been developed to model supernova spectra. So it's a free open source Monte Carlo radiative transfer spectral synthesis code to model the supernova ejecta in 1D models, not in 2D. It's just a 1D model because here we just want to simulate the light. So it is designed for rapid spectral modeling of supernova. So it is developed and maintained by many software engineers, computer scientists, statisticians, and astrophysicists. So here's the link for TARDIS, which is available on GitHub. You can see on the screen. You can go through the link and download TARDIS and then play around with the TARDIS code. All the informations are given on this GitHub page. Now, over to you, Garini. You can continue.
Okay, thank you, Shubham. Where you use TARDIS, TARDIS made exploring supernova easy, and from TARDIS is to develop a free and open source software tools for studying and simulating astronomical transients such as supernova and kilonova for academic and research reasons. TARDIS can be used for rapid modeling of supernova and other transients. It just simulates light so that we get something that can be compared with the observation. Okay, next. Okay. How TARDIS works? Used for radiative transfer equation in a relatively simple manner. How much intensity goes down from a given wavelength, and that's the cross section from non-atomic structure values, and calculates from a temperature how many atoms are in what level, and runs group of photon through an body star. Use this to update the temperature and finds a solution for the light field and state of the matter, and then produce spectrum.
Okay, thank you, Shubham and Garini. Now, in this slide, we will discuss the tutorial of the TARDIS. So, simply, we use the quick start tutorial from the TARDIS sn.github.io. So, simply saying, the TARDIS is a 1D model, which means we assume the homologous expansion. And what TARDIS simulation does is it picks a time, it picks a luminosity, it solves the plasma states, it deals also with important packets, it uses frequency and energy, and we can talk the Monte Carlo packets as a packets of many photons. And let's take a sample from a black body. It has a radiation matter interaction, it has a bound-bound interaction, it has also the Thomson scattering, bound-free, and also the free-free bound. And the outcome, it exists through the outer boundary constellate spectrum, and exits through the inner boundary or absorbed and discarded, and it gives the estimation of the temperature. And the Monte Carlo is simply a spectrum estimators. It keeps updating the model. If it is too luminous, it'll be a killer black body. If it's too faint, it will be a hotter black body. And basically updating the temperature or dilution factor until it finds the estimation of radiation field. Next. So then this slide, we'll discuss what the Q-star simulation results. So for every simulation run, it hits the atomic data and configuration files. There are 4 steps. The first, it import the atomic data, which we call in the .h5 extension. 2, we add a configuration file, which calls the target example.yml. And thirdly, we run the simulation. And fourthly, we're plotting the spectrum. So in configuration file, simply we define a luminosity of Sn with how many days of explosion we want to simulate, the atomic data file, the structure of the Sn, and in the start of the beginning of the Sn, and also the stop, which is the outer shell of the Sn, the number of shells or the num, the abundances, and how to simulate the plasma, and how we want to run the Monte Carlo simulation, and etc. In running the simulation, we'll be calculating the radiation field, the number density, running this packet simulated through the simulation. So next, we will take it from my friend. So please.
Okay. Next, we will see the result of the simulation, in which the output is graphs. So we see 2 graphs in which the left shows the radiation field updating through the envelope of the supernovae. The y-axis parameter is the temperature, and then in Kelvin, and then the x-axis is for the velocity. So each line represents the iterations, and then it went from the left to the right, each shell, and then it predicts the next temperature and the next velocity, and then in the right graph is the convergence rate versus velocity. So the y-axis is convergence rate, while the velocity is in km per second. And then we see with the convergence rate how the simulation is converging to find the solution of each iteration. Each line is also an iteration. It's the same as the left graph. And then next, then we see here top to the bottom, in which top is the inner boundary temperature graph, and then in the middle it's the luminosity for immediate luminosity, absorbed luminosity, and requested luminosity. And for the bottom graph is the residual luminosity. Yeah, next. All right.
So thanks, Farah. So for the third plot, this is the TARDIS example model spectrum. And the integrated spectrum calculated in 3 different ways: normal packets, virtual packets, formal integrals, and all are consistent with each other. And then after this, which can be compared with the observations. And what is normal packets? The first and most simple way in which TARDIS calculates spectra is by calculating it directly from the Monte Carlo packets after the final Monte Carlo iteration. This simply requires knowledge of each packet's energy and frequency in the lab at the end of iteration. The only other quantity needed is the time duration of the simulation delta t, which is calculated based off of the luminosity of the supernova's photosphere. And since TARDIS is a time-independent radiative transfer scheme, delta t should be interpreted as the physical duration of the emission process at the photosphere. And for virtual packets, a new population of Monte Carlo packets is introduced. Every time a real packet is launched or performs a physical interaction, a predefined number of virtual packets, or NV, are generated. This propagation of these virtual packets is followed in a similar fashion to the real ones, with the important distinction that their trajectory is never changed. However, the optical depth the virtual packet accumulates during its propagation to the ejecta surface due to electron scattering and atomic line interactions is tracked. Once the virtual packet escapes, its contribution to the spectrum is then weighted by this total optical depth. And for the last one, the formal integral, it describes an alternative method for calculating the TARDIS spectrum while eliminating nearly all Monte Carlo noise. Instead of calculating the spectrum directly from the Monte Carlo or virtual packets, we use information from the Monte Carlo simulation to build an analytical solution for the supernova spectrum. And this is just homologous expansion in the modeling, no shock waves included. Over to you, Laura.
Thank you, Haru. The reference we used for our assignment and presentation are the official TARDIS website and the TARDIS Quick Start Guide. And also, please next. We are very grateful for participating in IVC firstly, and secondly, we would like to express our gratitude to Institute Technology Bandung, Badan Resident Inovasi Nasional, to our organizers, lecturers, and our group members, and actually to our member group mentor Nisa and all other tutors. So thank you for your attention and your time. And if you have any questions, please ask us.
Okay, maybe I have a question.
Yes,
Can you
please.
show the spectrum again? The spectrum slide, maybe. Yeah, this one. I'm wondering, what kind of information can we extract from obtaining this simulation? Let's say I have observed a supernova and collect its spectrum and then compare it with this example maybe. What kind of information can I extract?
Okay, so I can tell you, maybe I might need to share my screen. So, okay, so in this graph, as you can see, yeah, okay. So in this graph, as you can see, we are simulating the spectrum, right? So can annotate, right? Can I annotate here? Like, yeah. Anyways, I'll share my screen. Haru, can you stop sharing?
Okay, okay.
Maybe I can annotate that. Okay, so yeah, I can do that. Okay, so this is the graph from the tutorial itself. So as you can see, there are these absorption features and here as well. Okay, so this is the prominent silicon line. So these are different methods how we are simulating the spectra. But if we see only one method, let's say we are not simulating with these two and just plotting with one method, we can see different absorption features and emission features, and we can compare it with the observations that how well we have simulated. So as I'm not sure. Okay, so it's from the this configuration file, if you see. Okay, so we are defining the abundances of metals, right? The magnesium, silicon, sulfur, and others matter. Okay, so in the plot we see those abundances. So in this particular wavelength, it's something 6,000 and something, we see the silicon absorption feature, and we also will see the other metal absorption features. So this is the information we'll get from this spectrum basically, and we can change this spectrum accordingly if we change the abundances, and we can try to make a better or make a like simulate a better spectrum to match our observations. Does that answer your question?
Okay, thank you for the answer. Maybe that answer a bit for my question. Thank you.
You asked, yeah, okay, thank you.
No, the time is not too much.
Maybe one more question, if there's any. A short one at that.
Maybe
All
I
right.
can add, but you can correct me if I'm wrong, but as it goes with spectroscopy, we see the elements in the supernova that we observe. So say that we don't know the type of the supernova, we can classify it as supernova type 1A or 1B or even 2. And if it's 1A, we can even use its standard candles. So I think one of the benefit of looking this spectra is to know the classification and the characterization of the supernovae. But you can correct me if I'm wrong. Yeah, thank you.
Okay, thank you for the additional explanations. And I think that will wrap up this session or this turn. So let's give applause to group, what was it again? 5, I think, right? Yeah, okay. Thank you. Thank you, group 5, for the really nice presentation. So let's go next to the next group. Who was it? After group 5, all right, we have group 2. Go up on stage. Are you ready for the presentation, group 2?
Yes.
All right. So yeah, please get ready. And once you're ready, you can start right away with your presentation. Who will share the screen? Okay. Right, we're still waiting to see your screen. Perfect, thank you. So please start group 5. The screen is yours.
All right, so Assalamualaikum. My name is Mugat and I'll be representing group 2 for the start of my topic presentation, which is about planning, modeling, and computational work based on Cepheid variable stars. Okay, next slide, please. So Cepheid variable stars, let me start off with how we're going to set up a numerical experiment. So the steps are, of course, we're going to look at the physical phenomena itself. What are Cepheid stars? What are Cepheid variable stars? And what the mathematical model is, and how we discretize the mathematics of it. Next slide, please. After that part of mathematics, of course, we'll select a numerical algorithm so that we can develop a computer program for us to implement an experiment to see how we use the observational data. Okay, next slide, please. So for my part, I will be presenting about the physical phenomena of Cepheid variable stars. So Cepheid variable stars are pulsating stars which are important in determining distances in space. Next slide, please. So you might ask, what is it and where was it first discovered? So they were first discovered in the Magellanic Clouds. Next slide, please. So the Magellanic Clouds, this is the large Magellanic Cloud. And then on the next slide, this is the small Magellanic Cloud. They're neighboring galaxies that orbit our Milky Way, which is kind of cool. So Cepheid variables, they were discovered by a person named Henrietta Swan-Leavitt in 1912. And she was working as a computer. She discovered that the stars were special because due to its pulsating brightness, it dims and it brightens again over a standard period of time. So she was a computer and was tasked to examine photographic plates. Back then, we didn't use CCD cameras or even films. And they were used to catalog stars. So the variability of these Cepheid variables, as I said, they dim and brighten and dim again in a steady periodic manner. Next slide, please. So this is an old data sheet from way back when they used to use, handwritten graphing methods. As you can see over here on the left side and on the right side, this is just the magnitude over a period of time. On the top there, you can see it's over 7 days, a week for one slice. So the magnitude changes from day 0 at the point A on the second slide. You can see it goes up sharply at day 5 and day 6, and then it drops down to day 7 and day 8. So after a week, you can see it brightens up, and then after by the end of the week, it drops down to be dim again, very dark. Next slide, please. So that was an old data. Now we can see this new data currently everywhere on the internet. Actually, this is Delta Cepheid data, which is actually just another name for classical Cepheid variable stars. Classical Cepheid variable stars are what we are going to observe today, and which is the original traditional variable stars that were founded by Henrietta and a lot of other more people. So next slide, please. So Cepheid variables, like I said, they pulsate in brightness. It's because they spin and they have a pole where it shoots gases that can be illuminated. So it spins, and of course, when it spins, the brightness is, you can imagine it like a torchlight. It brightens and darkens, and also pulsates in temperature, which is interesting. When you pulsate in temperature, of course, you pulsate with energy, and when it relates to energy, it pulsates in the size of the star itself. Since they spin very, very fast, they can change in size and elongate to up to 25%. So from a small blob of a star, it can be like as if it's a turtle egg, you know, an elongated egg. So the brighter the Cepheid, the longer the period. This is what Henrietta found actually, which is her law now, the Henrietta law. The brighter it is, the longer the period. So Cepheid periods can be in a span of a few days, like we just saw just now, just like 5-6 days, and up to a few weeks, and even hundreds of days. And it's also a great tool for determining extragalactic distances, which is very far from our own local group of galaxies. It's also used for the original way of calculating the Hubble constant for the expansion of the universe. All right. So this is the relation that I said about Henrietta's law, where you can see the luminosity or the magnitude of the luminosity even. It is a linear line where it is directly proportional to the number of days. So the brighter it is, of course, the longer the period is. I think that's all from me. I'll pass it to my friend.
So the next step is in actually making a mathematical model of the Cepheid variable. Next slide, please. And so building up on the previous explanation on the Cepheid variable, we're going to look at its pulsation period. And to do so, we first need to come up with a mathematical plan to suitably model the Cepheid magnitude data that we're going to observe. And so we know that our data is time varying. Therefore, the best way to work with it is to use time series analysis. Next slide, please. So one of the most commonly used method of time series analysis is the Fourier analysis, which is basically a technique in representing a given set of numerical data or analytical functions using an infinite number of sine and cosine functions. And from that, we can also estimate the period of the variability by determining which functions are statistically significant. Moreover, we're going to use the Fourier transform so that we can also determine the amplitude and phases of the components. And so for people who aren't very familiar with the Fourier transform, it's basically a mathematical transform that decomposes the functions that depend on time or even space into functions that depend on frequency accordingly. Next slide, please. And so let's look at the equation that governs this Fourier transform. And so letting some function x with some respect to some function of t be a set of time varying data, the Fourier transform is given by the equation 1, in which it's a function of frequency, keeping in mind that frequency is also 1 over period. And we can also represent the complex component as seen in the exponential function using the Euler's formula in the second equation. And so now we have the mathematical model, and now it's time for us to discretize our models so that the computer can understand it.
Okay, so I will explain the third step. The third step is to discretize the mathematical model. So the mathematical model must be converted from a continuous or differential equation, in this case, the Fourier transform, into an algebraic approximation so that it can be solved by the computer. So to develop the computer program to find position period of separate variables, we have to discretize the Fourier transformation formula. In this project, we use the DFT or discrete Fourier transform in developing the computer program. Why? Because the DFT is usually considered as one of the most powerful tools in digital signal processing because it can transform a sequence of evenly spaced signal to the information about the frequency of all the sine waves that is needed to sum to the time domain signal. DFT are extremely useful because they also reveal some periodicities in the input data as well, as well as the relative strength of any periodic component. Since DFT deals with a finite amount of data, it can be implemented in computers by numerical algorithms or even another dedicated hardware. So the DFT is defined by the equation 3, where n is number of samples, the big N, the small n is current sample, k is current frequency, xn is the sign value at sample n, xk is the DFT, which in itself include information of both amplitude and phase. You can notice that this function is different than the previous Fourier transformation equation, and this one can be processed by the computer. So after we apply the DFT and we get the result, we can get some information such as amplitude and phase of the signal, which can be calculated by using these two formula, where imaginary xk and real xk are just like the name, the imaginary and real part of the complex number, and A102 is a two-argument form of the acting function. This information will be very important for our next processing information. Okay, next.
Okay. After we discretize the mathematics, the next step is making the selection of numerical algorithm. We need to be able to solve the discrete problem rapidly on our computer by selecting and putting the numerical algorithm in the proper order. So here we show the algorithm in a simple flowchart. We start from the rounded corner box in the upper left. First, we import the data consisting of the epoch and Julian date, the apparent magnitudes, and the uncertainties. Second, we define the DFT function and then calculate them. Next, we set the step rate and calculate the frequency, and then we calculate the amplitude. We have frequency and amplitude, so we make the frequency amplitude plot. We now have the plot and its peak frequency. After that, we calculate the period using the expression period equals to 1 over frequency, so that we can make the phase magnitude plot, or in other words, the light curve. And then we have the phase magnitude plot, and so it's finished. Next, Hafiz will go to the fifth step, developing the computer program.
Okay, after that, we develop the computer program. This is the computer program based on the previous numerical algorithm. So first we import the module and import the data. Next, and then we define the DFT function. Next, and after that we calculate the DFT and we set the step rate and calculate the frequency. Next, then we calculate the amplitude. Next, then we plot the frequency amplitude. After that, we calculate the period from k, and then after we get the period, we make the phase magnitude plot. Next, after we have a code, we are doing a computer experiment. Next, so we use that code for the first separate in Andromeda Galaxy. And we get the data from VSO. We use the data observation in 2016. So this is the result. Its frequency is about 3.5 196 exponent minus 2, and its period is about 31.285 days. Next. And then we made the phase magnitude plot. So this is the light curve of M31V1. Next.
Okay. Finally, we would like to show everyone our future plan. Everyone can hear me, right? Is everyone can hear me?
Yes, yes.
Yes, perfectly.
Okay, thank you. So finally, we would like to show everyone our future plan. We would like to use MESA code with the addition of Jaya module provided also in the MESA. The module will compute the stellar structure of our Cephide star from the pre-main sequence to the predicted Cephide age, just like we did in MESA class with Dr. Nurhaliza. But this time also compute solution of perturbed simple spherical harmonic oscillator in terms of periodic eigenfunctions. To understand what I talk about, take a look at the orange star picture there. The convective core inside is pulsating with G modes and radiated to surface layer with P modes, frequencies producing the variable pulsation that we observe today. So the computation in the star modeling will work out the harmonic frequencies over the time step dt, giving us the stellar structure we can better understand. Next objective is to obtain the period spacing of the pulsation and compare it with our previous result. So to execute this, the parameters of the star like mass, composition, rotational rate will be used as our constraint in the stellar model. So that is our summary of the future plan. To add, this theoretical modeling is actually important as it will give us some confirmation about our understanding of the physics in the astroseismology so far. Okay, thank you. That's it for us from us. Any questions? We can start working on the question.
Okay, maybe I can ask a question. I'm wondering about the data you're using. Is it how the data structure? Because we haven't seen it. Maybe you can explain.
Hello, can you hear the question?
Oh, okay. Can you hear me?
I wanna.
I'm wondering about the data structure. What's inside the data point?
Okay. Maybe I can share my data, but I will explain about the data. The data include the first is about Julian date, and then apparent magnitude. After that, there is an uncertainty, and there is observer. That's the data.
Oh, okay. I'm also wondering about the interval between each observation. Is it regular or irregular?
For the interval, I think it's irregular, but the observation is about from July until maybe October, I think.
Oh, okay. As far as I know, and in your slide, you're using discrete Fourier transform, which require the data to be regularly interval. The interval should be regular, but your data has a regular interval. How do you tackle that problem?
Okay. Actually, in 2016, the observation is from July until December. In the maybe in 3 months, there are many data, and the other the data is not much, not many. So we select the data when the data is we have enough data in that time.
Oh, okay. But that's not really my problem. The problem is you're using discrete Fourier transform, which required a regular interval in the time dimension, but the data you are using was irregularly observed. Maybe I can comment a bit about this problem. I have taken Mr. Hakim class and also did this experiment, and we were using a modified discrete Fourier transform. It was called date compensated discrete Fourier transform, DC-DFT. You can use it for irregular interval. That's all I can add. Thank you.
Yeah, thank you.
Any more questions? We still have about 1 minute left.
Yeah, can I have just a short comments, maybe?
Yeah,
Yeah.
please. Maybe keep it short. Thank you.
Yeah, regarding the question of Ali, yeah, maybe why we need to make sure that our data is regular for DFT, because if not, there will be an artifact in the frequency domain. So you can see a lot of, you see in your plot, there's a lot of signal, not signal. Yeah, there's a lot of yeah, like peak.
You mean chunks?
You see, in your yeah, very clear what is the period of the surface, right? You see, there's a lot of version of the amplitude. Yeah, there is a highest one, but there is a lot of smaller one, and it's because there is an artifact, as far as I know, that produced because you the data is not regularly sampled. Maybe a most simple way to avoid this problem is to use a moving average method. It's a simple one rather than the DESI Ali said. Yeah, it's just you make average, moving average. You see, you make, for example, you make a windows like 1 week or 1 month, and you moving the windows and you calculate each windows the amplitude of the signal, and by doing that you can make sure that your data is equally sampled, and just doing you can doing the analysis by using the FT. But of course, this simple method has a limitation for the complex data. But if you have data with really with a simple period, I mean just one period, as you saw us earlier, yeah, it's simple, just doing a moving average, and your data will be perfectly regularly sampled. Yeah, that's just my comment.
Okay, thank you, Dr. Ibnu, for the comment. And well, let's give a round of applause for this group after the very nice presentation. Thank you for the presentation. Okay, so, oh, I'm sorry for the background noise. Okay, so I know that group 3 can't wait to present your project soon, but I think here comes the break time, right? The host team, I believe. Okay, I think that's a yes. Let's take that as yes. Yep. Okay, thank you. So we will have like a short break for about 10 to 15 minutes. So thank you everyone for the presentation for the first session, and we will have the next session after the break. So let's get back